down. There we go. Okay, hopefully that stabilizes. Sorry about that. Yeah, what I was saying is if we see this curve as being the frequencies of each of our data points in a continuous set of data, then we can say that the parts that are small or very low right here are very low frequencies, so data that doesn't happen very often. Whereas in the middle, where it's highest at its peak, is the data that happens the most often, which, like we said last time, represents our mode. However, we also said that if it is normally distributed, something like this, where we have a nice single curve, it goes right up like that and then right back down, it's like two peaks or things like that, then we can also say that this is the median, which of course means that it splits our data into two equal parts, as well as the mean, or the average data. Okay, so that one single point in the normally distributed set of data represents these three things: mode, median, and mean. And lucky for us, if we have normally distributed data, then we can use this idea to our advantage to learn more about where our data is actually located within this curve. In particular, if we want to know something like how much of the data falls behind this point right here, whatever x value this might be, then we can use a little bit of math, not even really complicated math, to find this entire shaded area. So find a percent. So again, what we're doing here with what we call really the empirical rule is we are finding the percent of data that falls behind a particular point. Now, this also gives us some opportunity for probability, because if we think about this as a real-world set of data, something like last time when we were talking about the light bulbs, then we can choose one of those light bulbs off of the assembly line and figure out what the probability is for that thing to have a certain lifespan. Okay? So let me just give us some numbers here real quick. First of all, our z-score equals x minus mu divided by sigma, the standard deviation. So we need our mu, which is our mean. We need our sigma, again, our standard deviation. And we also need an x value to look at. Again, this x value is whatever point we're looking at on this curve. So I'll just give us some information here. Let's say we have a mean of 25, a standard deviation of maybe 0.2, and since we're looking at a x value that's above our mean, let's choose something like 40. Okay. So once we have this information, we can just go ahead and plug it into our formula. I'm going to zoom that in a little bit. So, plugging this in, we get z equals, let's see, x is 40, so 40 minus mu, which is 25, divided by sigma, which we said is 0.2. Okay, so we just need to kind of do our math here. So the top part there, 40 minus 25, let's see, we get 40 minus 25, we are 15. So z equals 15 divided by 0.2. And we get, that doesn't make sense. What have I chosen that's wrong? By the way, y'all are my guinea pig class. I figure out these numbers for y'all. Okay, let's just choose some new numbers, some that I know will work. Mu is equal to 70, sigma is equal to, let's say 10, and then our x, let's do one that's lower. How about 50? Okay. So let's try this one then. Z equals, let's see, 50 minus 70 over 10. A lot easier numbers for us this time. So 50 minus 70 is going to be what? Positive or negative? Negative, yeah. And in fact, 50 minus 70 is negative what? 20, yeah. So now we have z equals 20 over 10. Okay. So what is 20 divided by 10? 2. Yeah. Now that makes a lot more sense. Oh, whoops, that should be negative. Okay, so we get a z-score of -2. And what we need to do now is we need to take our table. Again, we have a negative z value, so that's the second table. Has all the negative z values on it. And find -2. Okay, so -2, and then there's no decimal behind it really, so 0, so -2 and 0.0. We scroll down and we find we have a probability of 0.02275. Okay, which if we were to make that into a percent, of course we take that decimal, move it twice, that our percent is 2.275%. Any questions? No questions? Okay. So, the other thing that we said that we could do is not just calculate lower than a particular x value. We can also calculate for what percent is above that. So let's go ahead and do that here. So what we just calculated is something like this. So our x value is about right here. We just calculated this area right here. Again, this is behind our x value, which in this case was 50. If we want to calculate above that, we need to remember that the entire data would represent a probability of 1. I mean, if you have the entire thing to choose from, what's the probability that you're going to choose one of the data points in the set? We have the entire set, so the probability is 100%, or 1. So if we have the probability of picking one from this side, all we need to do is subtract this part from the rest, and it'll give us what this is. Okay, we're just kind of like breaking off this piece and seeing what's left over. So we take 1 minus this probability, 0.02275, and let's again go ahead and figure that one out. So 1 minus 0.02275, and we get that the other side would be a probability of 0.97725, or again as a percent, that would be 97.725%. Okay, so any questions? All right, now for this next one, let me just look up some numbers so that I know that I have something that'll work. Let's see. Okay, yeah, I'm just going to have to use that. So I left you off with this on Wednesday. We know how to calculate above, and we know how to calculate below. So can we calculate not above or below, but in between? So I'm going to say something like this. So we don't want to know anything except for this shaded area right here. That's the only part that we want to know. Okay, well, let's think about this a little bit. With our previous example, again, the first thing that we calculated was, okay, what is the probability of a data point lying below this point, right? And then we said, well, what if we don't want to know that, but we want to know this other side, above? Well, what we did is we broke this piece off to give us what was left over, right? In fact, we can do that with this as well. If this is what we want to know, then what we can do is we can find the areas or the probabilities of these sides instead, everything that isn't what we want, and subtract it from the whole to just give us what's left over. Just like we were doing to find the stuff above a certain x value. So let's try this out. Okay, so let's say we have a mean, or mu, of, let's say 72. That sounds like a good number. And a standard deviation, sigma, of 2. And now we need to know what x values we're looking at. So let's say that this one here is 34. And this one right here is something like 60. Okay. Like I was saying before, what we need to do here really is not calculate anything about between here, but calculate the stuff that is outside of it so that we can take it away from the whole and just be left with what we want. So really, we're going to need to calculate two of these things. We're going to need to calculate the area of this side and the area of this side. So let's go ahead and set that up. So z equals, let's set up this one here. That'll be 34 minus the mean, 72, divided by sigma, 2. And then this one here is z equals 60 minus the mean, 72, over the standard deviation 2. You know what, I'm going to change this one here. Let's make it 54. Close that range a little bit. Okay, so let's go ahead and calculate these. 54 minus 72 is negative 18, and then divide that by 2, we get negative 9, which unfortunately is actually still way too small. That's like right over here. There's basically 0 data points over there. So let me change this again. Let's see. Let's do 65 and 69. Close it even more. Okay. So z equals 65 minus 72 over 2. And z equals 69 minus 72 over 2. So 65 minus 72 divided by 2 is negative 3.5. And then the second one, 69 minus 72 divided by 2 is 1.5, negative 1.5. All right, there we go. So again, we have negative z values, so we need to look at our negative z chart. And let's remember what each of these is doing once we look these up. So negative 3.5 is right here. Negative 3.5, and there's no decimal after that 5, so we can just go ahead with this one. That's 0.00023. Hardly any data behind that. Then our other one, negative 1.5, is right here. Again, there's no decimals after that 1.5, so we can go ahead with 0.06681. But again, we need to think about what we actually have here. So I'm going to draw smaller versions of these frequencies so we can kind of imagine what these look like. Now this one has calculated everything behind it, and this one has also calculated everything behind it. Okay, so this one also looks like this. Okay, now this side's fine. We want to get rid of this part, right? But this side isn't quite what we need. It's everything back here, including this and this. We don't want that. We want this side. So what do we need to do with this number? Yeah, subtract it from 1. Again, if it's calculating everything behind it, we want to reverse that and make it go everything above it. So we are going to subtract it from 1. So this one, again, is fine. It's calculating the right thing. It's just this one that we need to change and flip to this side. So let's go ahead and do that. 1 minus 0.06681. And let's see, that gives us, if we change this, 0.93319. Okay, so now we have the other side. So again, if we think about it, this whole side right here is 0.93319, and this side right here is 0.00023. And that's the stuff we don't want. So what do we need to do now? Yeah, subtract them from 1, both of them from 1. So what we need to do is 1 minus this one, 0.00023, and then minus another 0.93319. So let me go ahead into my calculator. So 1 minus 0.00023, and then minus another 0.93319. And so this gives us 0.06658. Or of course, as a percent, that would mean that we have 6.658% of our data in this range. Does that make sense? Yes? Okay, good. Any questions? None? All right, good. So I got one more thing to show you before we go today. Okay? Same idea. Normal distribution. And of course, mean, median, and mode are all there in the middle. And I've got an x value here, but I don't know what the x value is in this one. Instead, what I know for this one is the probability. So all I'm given is the probability of this area. And apparently, this area has a probability of 0.99224. And what I want to know is I want to know what this x value is. What is that? Okay, so can I find it? Kind of. With the information that I'm given here, I can kind of find it. And let me show you what I mean. So let's think about this. We know how to go from an x value to a probability. So it makes sense that to go from a probability to an x value, we just need to go the opposite direction, right? So let's see. This is a really, really big probability, so it's probably going to be a positive value. So we need to find this probability somewhere in this chart. Okay? So let's see here. We have 0.99, so we need to find where we have 99. And we've got some 99s around here. And then 224. So right there. Oh, yeah, just barely off. So we got 0.99224 right here. So what we do now is we just look and see what z-score that equates to. So let's see, 2.42. So we know our z equals 2.42. Now we also know that z equals x minus mu over sigma, right? So what we can say here is, well, okay, if this is what x is, we just plug it in for x. So 2.42 is equal to x minus mu divided by sigma. Now again, I said that we can kind of figure out what the x value is, just given the probability. We don't know the exact thing because we need to have more information here. We need to know our mu and sigma, which if we have the actual data we could calculate, sure. But for the purposes of this problem, let's just find the equation that gives us x. So what we're going to need to do here is get x by itself. We're going to need to take everything that is not an x and bring it over to the other side, cancel it out. Okay, so what's the first thing that we think we could do to cancel out a number on this side? Well, that fraction's looking pretty annoying, at least to me. So let's get rid of that fraction. How would we get rid of sigma? Right now we're dividing everything by sigma, so what's the opposite? Yeah, multiply. So multiply everything on both sides by sigma. And so now what we get, if we multiply this number by sigma, we basically just have 2.42 sigma. Okay, and then that's equal to whatever's left over, so x minus mu. Okay, again, we want to get x by itself, so what's the next thing we can do to try to get it by itself? Yeah, add mu to both sides. Okay, so that's going to cancel there and give us 2.42 sigma plus mu equals x. And this is as far as we can go. Again, if we knew sigma and mu, then we could plug those in right here and here and get our x. But in this case, we don't know them. So this is as close as we can get. And I'm showing this to you because I know Hawks has that on there. And I know it has given people problems in the past because they're always looking for, where's sigma and mu? It doesn't give me sigma and mu. How do I find them? It doesn't want them. It wants this. Okay? Any questions? None? All right. Well, I think that will do it for today. So, next week, remember that Wednesday is a holiday. There's no class on Wednesday. Expect a quiz next week, and it's going to be over this stuff. Okay, this empirical rule stuff. So no. Yes, I want you to keep those. Those are for you. And you'll want to have those for when you take the quiz. Now also I did email out digital copies of those so that you can have them anywhere you go as long as you have a computer. Okay? But I do want you to have those for when you take the quiz because obviously you're going to need them. Alright? But expect a quiz next week and I will see y'all on Monday. You too.